Good morning to all. Today we are going to describe a matching circuit that we have developed using a stub, and we will demonstrate that design in two different ways. One by using transmission line equations and concepts, and then second by using the Smith chart. So let us assume that we have a transmission line that you can see here. At the end is the line is connected to a load that is equal to 200 plus J100 ohms. And this load now is connected to this line that has characteristic impedance of 50 ohms. And what we want to do is to place a stub at a distance D1 from the load. And we have assumed that this is an open circuited stub. We want to find its length, D sub 2, in addition, of course, to the distance from the load D1, so that the line at BB prime is totally matched. What that really means is that the reflection coefficient at BB prime is 0, as you can see here. Now, let us try to solve this problem using the transmission line equations that we have seen and utilized extensively. To simplify things, and considering that all of the characteristic impedances are 50 ohms, first of all, what we do is to normalize the load with respect to the characteristic impedance, and that makes it 4 plus J2. And then what we do in figure 1 is to go to point C prime and to look toward the load. That point is to the right of the stub, so we have the stub behind us, don't see it. We just see a transmission line of length D1 that is terminated at CL, and at CC prime, the input impedance that we see because of that termination of the line is Z input at CC prime. And according to the equations that we have derived and used so far, here this normalized input impedance at CC prime is given by this equation. Now, we place that impedance there. If we go and now look toward the stub from BB prime, what we are going to see is an equivalent impedance Z sub S that comes from this open circuited stub, which has a length D2. And according to what we have derived so far, this equivalent, or normalized, I should say, stub impedance is given by minus J cotangent of beta D2. So now we place the two impedances right there. As you can see, both normalized. And the combination, the parallel combination of these two impedances gives us nothing else but a total impedance that you see at that point on the line. And this total impedance has to be equal to the characteristic impedance of the line, Z0, so that this reflection coefficient at this point becomes 0. To simplify things, and because these two impedances are in parallel, what we do is to convert those into admittances. So if you have two admittances in parallel, the total admittance then becomes the sum of the two. And how do we find those normalized admittances? They are the inverse of the corresponding normalized impedances. Okay? So having that into consideration, and here we wrote all of the equations we have for Z sub S normalized. This one, in fact, the first one is not normalized, and we normalize and we get this expression here. And from there, we get the normalized admittance for the stub, which is equal to this one. And we do the same for the input impedance and CC prime. And we normalize it next, and then we get the inverse of that, and that gives us the input admittance normalized at CC prime. And we place those two expressions here, we sum them up, and they give us the total admittance. To be able to have a total matched at BB prime, we need to make that reflection at that point 0, which means that both normalized impedance, total impedance at that point, and normalized total admittance at that point have to be equal to 1. This is the matching condition. Now, to simplify our expressions further, we will see later that we are replacing the tangent beta d1 with x and the tangent beta d2 with y. So now we take this equation that you see here and we replace ZL, or we can use it in terms of YL, as you can see here in 2. It doesn't matter, both of them will give the same result. And I will start working on Z2, so the equivalent YL normalized for ZL, which is 4 plus J2 normalized, is this one, 0.2 minus J0.1. And then we replace that into equation 2. We make the total, the sum of the two, to be 1. We assume that X equals tangent beta D, Y equals tangent beta D2. We replace those into 2, and we get a complex equation, which is this one here, or this one, if you want to work on this further. Then this complex equation gives us 2 real equations. One that shows that the real part of these 2 complex numbers, this one and this one, have to be equal. And the second, that the imaginary part of these 2 complex numbers, this one and this one, have to be equal. Okay, so we get these 2 equations, A and B. We solve these equations and we get that y equals minus the ratio of 8 plus x divided by 2x. We take this expression for y, we plug it into B, equation B, and after some simplifications, this gives us this second order equation, which in fact a quadrature equation. It gives us 2 values for x. Okay, and these 2 values for x, x1 and x2, will give us 2 values for d1 and for d1. And so this is the d11, if you like. This is the d12 value. And by plugging in from the x values, we find 2 values for y, which gives us 2 values for d2. So now we have 2 pairs of solutions here. The first D1 corresponding to the first D2, the second D1 corresponding to the second D2. Okay, so 2 solutions to the problem. Now, let us try to solve this using the Smith chart. We will do pretty much the same, but on a Smith chart. So what we do here, we start with point A. In fact, point A here, ZL, not A yet, ZL. This is the normalized impedance. According to what we have discussed and also notes that you will find in your book, to convert using the Smith chart a normalized impedance into a normalized admittance, what you do is you draw from there the constant VSWR circle. From this, then you draw a diameter for the circle that starts at point ZL normalized, goes through the center of the circle, goes to the other, you find the anti-diametric point, and that's your normalized YL. And when you measure it from here, the normalized YL, this is exactly what we found analytically, is 0.2 minus J 0.1, which is here. Then what we do is the following, the way we think. Now, we have to move along this line up until we place the stub. So we are moving along the constant VSWR circle, which is equivalent to moving along the transmission line. And we are going to move by a distance, D1. So we're going to move until we find a point. But how do we know which point is that? This is the point where our constant VSWR circle intersects the resistive circle that goes through the center of the Smith chart. Now, what is the characteristic of that specific circle? All the points on this circle, they have a normalized real part, which is 1. So practically at this point, we have a normalized input admittance at C prime, which is represented by A, and this here, I don't have it normalized, we'll put a normalized admittance and input admittance at CC prime, which in fact has a real part equal to 1. Now, why do we stop there? Because we know that an open-ended stub cannot really change the real part of the admittance, because an open-ended stub has an input admittance, or an input impedance for that matter, which is purely reactive. So when you normalize the YS or ZS, which is the normal impedance or normal admittance of normalized of the stub, what you find is there's a purely reactive number. So it's going to only affect the imaginary part of the normalized input admittance at CC prime. So what that means is that if it only changes the reactive part of this input admittance, then I will need to find a place to stop and place the stub where the real part of this normalized input admittance is 1. So I found that, it's A. Then from A, I have to move down. You see, from A, I'm going down until I find the center of the chart. So practically, I need to find a Z sub S or a Y sub S, normalized obviously here, that is going to get me to the center of the Smith chart. How are we going to find that? That's easy. Since we found this point A, I can read from here, from the chart, what is the value of the normalized input admittance at CC prime. So practically it's going to be 1.8, this point, 1 plus J 1.8 normalized. So here it is. Y input at CC prime, you see it here. You see it here is 1 plus J 1.8. And the distance that I've traveled to place, to find this point, D1, how do I find this distance? Is by extending these two lines that connect the center of the stub to this point here. And then I connect also the center of the Smith chart to A, and then here. And because I have to move practically from, this is my starting point, that's my normalized admittance load. And I have to move there and move enough, long enough, until I get to this point A. So the distance that I have to move is going to be given by the number I'm reading here, which is 1.85 plus, and this is from here, right? This is where it starts at 0, plus this distance here, and the sum of the two will give us D1. So what we found is that D1 is approximately 0.2. Okay. Then we want to find D2. Now from here, from this expression, we see that we have a reactive part in the normalized input admittance at CC prime, which is equal to J1.8. And thus we want to cancel with the stub admittance. So from here, you see that we want to add these two and get y sub t equals 1, which makes y sub s normalized, the normalized admittance of the stub, to be minus J1.8. How now are we going to find that point? So the stub is open circuit. When you have an admittance for an impedance, that open circuit translates into infinite, large. For an admittance, translates into 0. So we have to start at 0. That represents the load of the stub on the Smith chart. And it's 0. 0 reactance, all right? 0 reactive part. And then, and 0 resistive, obviously. That point has 0, total 0. Then we move along this VSWR for the stub. It's this VSWR circle. We move until we get to the point that gives us that minus 1.8. So it's capacitive because it's minus J, 1.8. And we stop there. And we measure this number here. We measure this number. And as a matter of fact, this number is going to be 0.33, close to. And what we find from here is exactly here. The D2 is equal to 0.332 lambda. Now, this is one of the two solutions. The other solution, if you want to find it, we're going to talk about the other one on Monday, but practically you keep traveling on the constant VSWR circle until you find the other side of the resistive circle, and you stop there, and so on. So we are going to find the other solution on Monday. However, here, we're going to remember the 0.2 and the 0.332 and see how close it goes to the solutions we have. And the two solutions we found here is D1 equals to 0.211 and D2 equals to 0.34 lambda. Now, the reason our solution, my solution practically on the Smith chart, is not exactly 0.34 and it's not like 0.21, is because the circles that I'm drawing, especially the VSWR circles, are not accurate the way I can do them on OneNote. And that's why it has a deviation. Otherwise, you will see that if I could use a compass and develop here the constant VSWR circle accurately, then I could do the values we could find the values to be much closer to the theoretical ones. But if you can see how much faster is to use the Smith chart to get this solution from this one, then you can imagine why people still prefer the Smith chart for solutions that can be fairly accurate. So with that one, I would like to stop here this lecture, and I will see you on Zoom on Monday. Take care.